So some of you probably saw the video that is posted already where I go over some of the big ideas about fracture mechanics and more specifically this idea that you can have materials, I guess I covered a few things, but you can have materials that have small little defects in them, and the process of those defects becoming large defects is kind of an interesting process. That's more or less what we're talking about when we talk about fracture mechanics, is that process of going from little small defects in a material up to larger ones, and ultimately the parts can actually fail completely. One of the things that you probably noticed in there is that we talked about energy, and that materials, if they can absorb more energy, that typically means that they are tougher against fracture, and that's where this idea of fracture toughness came from. So if you haven't seen that video already, I would encourage you at some point to go out there and watch it, because it's got some really good, interesting background information. I'm going to show you here today an example problem where we get down more into the nitty-gritty of what do we do with this, okay? And this is the specific problem that we're going to work, okay? So I'll kind of go through the problem statement here. This says, a titanium tubing manufacturer discovered an issue during a run of this titanium tubing with the dimensions that are shown there. The issue caused the tubing to have this little 0.76 millimeter deep longitudinal crack, and the way that we might know that is by measuring it with X-ray tools. It says the processing of this tubing has given it a yielding strength of 990 MPa. So let me explain that a little bit. Titanium is a material that responds pretty well to cold working, among other ways sometimes of strengthening it. And the idea there is that if you start with just plain titanium, it's not going to have yield strengths as high as if you cold work that titanium. But one of the things that happens when you cold work the titanium, it also gets more brittle as you begin to cold work it. It loses some of its ability to absorb energy. Okay, so this particular piece of titanium has been cold worked to the point where it has a yielding strength of 990 MPa, and we will look at what that means to us here in just a few minutes, okay? The manufacturer still wants to sell this tubing, but they want to advise the customer regarding the maximum recommended pressure capacity that they should put into this tubing, okay? So this is something that manufacturers do sometimes. You've spent the effort and time and money to be able to make a product, and if you discover a defect in it, you might still be able to sell it. You just have to advise the customer that this isn't as strong as one that didn't have the crack in it, right? So we're going to try to do something that somewhat mimics an exercise like that, and we'll try to figure out what the maximum pressure is that we actually can put into a tube like this, knowing that it has this crack in it, okay? It's going to be less than if it didn't have the crack, probably pretty obviously. All right, part A, it says determine the maximum allowable internal pressure at room temperature while maintaining a factor of safety of 3.5 against yielding and against catastrophic failure due to crack propagation. Okay, so this actually introduces another idea here, that there's more than one way to fail these materials. One way is what we're used to. You can cause some permanent deformation through yielding. Okay, so we will do that for this problem and kind of figure out, will it sort of yield on a macro scale? But then the other part of it has to do with whether or not the conditions are right for this crack to actually propagate through the piece of material. And that's kind of a new thing. We haven't really talked about that yet, and that's really the point of this problem, is we have some techniques that we can use to determine whether or not this crack is likely to propagate through the material and cause what is called in a lot of these reference materials catastrophic failure, which, I like that phrase, all right? Part B, it says, what yielding strength would have caused the potential for crack propagation to be equivalent to the potential for yielding? Okay, so what I'm asking for there in terms of the big picture is when we do part A, it's either going to yield first, or the potential for crack propagation might happen at a lower pressure than where we would expect it to yield. It could be one, it could be the other, that would kind of define a failure for this material, and we're going to figure out which one of those two would control for part A. For part B, we're going to look and see that we maybe could have prepared this material with a different amount of cold work, and it would have made the potential for both of those two possibilities equivalent to each other. Okay? So these are the big pictures that I'm trying to present first before we get into the details of this problem. With me so far? Okay. So before we get into the nitty-gritty of the math also, I'm going to mention this part too. You might remember that whenever you did some calculations regarding stress concentrations, like think of the classic one where you've got like a hole in a plate and then you pull on the ends of the plate. Weren't those the good old days when that's the kind of problems that you were working? Okay. So, think of that case and you calculated a nominal stress for that situation. When you calculated the nominal stress and you have this hole in the middle of a plate, what area did you use to calculate the nominal stress? In other words, the stress that you would have calculated before having the stress concentration. Yeah, so you would basically look at the plate and subtract the cross-sectional area that's gone because there's a hole in it, and you would use that as your nominal stress before even calculating a stress concentration factor. Okay? I'm going to mention this, that when you do these problems regarding this sort of possibility of catastrophic failure due to cracks, I've reviewed a good number of example problems that are out there, and it looks like some of the authors don't try to do a sort of an adjustment for the fact that once you have a crack in your part, that's less area that you have to actually carry stress. And there's a lot of example problems out there I've seen where it doesn't look like they did anything to try to account for the fact that there's less area due to the crack. And I'll just say that those authors who did those kinds of example problems may have a good reason for doing that. It just makes me uncomfortable. Because when I look at a problem like this, I look at that crack that's going down the length of this thing and I say, that looks to me like there is not material there to carry the tensile stress that is going to be caused by the tangential stress that's going to be carried in this tube when it's got internal pressure. Okay? So why don't you tell me, what do you think a way that we could use might be that we could basically derate this thing, kind of plan on it having less strength because that crack is actually sort of missing bonded material because there's a crack? What do you think we might be able to do? Yeah, so we can kind of count that outside radius, even though we have an outside radius here that's given of radius is 12 millimeters, right? We can sort of pretend like that outside radius is a little bit smaller, right? And that might be too conservative to think about it that way. Like we might overpredict what the stress would be in this case, but it's always safer to be a little more conservative, and especially if we're dealing with a design type of a situation. So that's what I'm going to suggest, is that we think of this thing, and maybe I'll make a little sketch here, but think about drawing like a little circle on here, right, and say all of the material to the outside of this little circle, we're going to pretend like it's not there, right? And we're only going to count the material to the inside of that circle when we're doing our stress calculations and such, okay? All right, so for part A, let's do the first part of part A, because A kind of has two parts to it, right? One of them is, let's figure out what kind of pressure it can hold to avoid yielding, okay? So let's do that down here. So part A, okay, we'll say maximum pressure while avoiding yielding. And this gets a little bit more safe too, because it says we still want to have a factor of safety of 3.5, even with this recommendation for pressure that we're about to give. Okay? Well, what's our definition for factor of safety that we always tend to use? Okay, our factor of safety here, I'll say sub y for against yielding. It is the stress that causes failure, right, divided by the stress that it's actually experiencing. What stress causes failure for this material in yielding? 990 MPa, so that goes in the numerator. Okay, what goes in the denominator? Okay, for convenience sake, I went ahead and copied the equation for tangential stress in this body. And by the way, I didn't really talk about this, but one of the things that you often should do if you're talking about a pressure vessel like this one is make sure that you're okay using a thick wall versus a thin wall formula. You like figure out whether you should maybe use the thin wall version of it. And by the way, on that, it's never necessarily wrong to use the thick wall version. It just sometimes makes it simpler if you use a thin wall version, okay? But for this one, how would we figure that out once we've derated this thing for the amount of area that's missing? Okay, you might remember that what you do is you take the wall thickness divided by the radius, right? And what value, when you take that wall thickness divided by the radius, you remember the value is sort of the threshold? It's about 1/10 or so, right? If the wall thickness is greater than about 1/10 of the radius, then you're going to be okay. So how do we check that? What's the wall thickness? Okay, 12 millimeters minus 10 millimeters. Okay, or should I use 12 millimeters? Okay, yeah, so 12 millimeters minus 0.76 millimeters, okay? And then the wall thickness I get by taking that and doing what with it? Subtracting 10 millimeters. And then all this gets divided by the radius of the thing, okay? And so for that, I might do a 12 millimeters minus 0.76 millimeters for that parameter. Anyway, if we plug this in, what we'll get is 0.11. And what does that tell us? That means we're a little bit too much wall thickness to feel good about using our thin-walled formulas for stress, okay? If this had been less than 0.1, we'd have felt better about maybe using a thin-walled approximation, okay? So, but you might have thought that that's where we'd end up because I went ahead and put this equation for the tangential stress on here, the equation 350, it's labeled down below there. And that one is for thick-walled vessels where you only have internal pressure. Okay? So what do we need to plug in for that equation? What's Ri? Okay. 10 millimeters, and that's squared. What's P? P is what we're trying to find, right? So I'll just leave it in there as a variable. Okay. I can call it PI if I want there. Divided by, what should I use for RO? Okay, 12 millimeters minus 0.76 millimeters. Okay, all that is squared, then what? Ri is 10 millimeters. Okay, that would be squared. Then what? 1 plus, okay, RO over R. What do I do with that R? Okay, someone says use RO. Okay, and instead of maybe the RO of 12 millimeters, what we're really talking about is the new RO that we're talking about out to the kind of radius of where the crack tip ends, right? So I agree with that, and so what you'd end up with there is actually that's the value you'd use for both of these R's, right? Which, by the way, I can keep writing it this way, but it turns out to be 11.24 millimeters, okay? that would be that squared over 11.24 millimeters squared. And I write all that out on purpose to make a point. What is that point? Okay, yeah, all of that right there is just 1. So all of the stuff in the parentheses, right, all of this stuff right here, what is that factor? It's just 2. So I might not always write all of that out for all of the equations that I do today, because that's typically what they're all going to be, is that factor over there is just going to calculate to 2, since what we're doing is we're picking a radius that gets us to the bottom of the crack tip, right? That's where we're trying to evaluate this stress. That's likely where this worst case stress might be in any case. Okay, what do I do with all this? Okay, I actually know what factor of safety I'm shooting for, right? So I plug that in for my factor of safety, and I solve for P, okay? Which I won't do that. I won't spend the time doing, like, punching it into the calculator and everything. But if you do, what comes out of here is P sub I is going to be equal to 37.249 MPa. All right. Nice little warm-up. So that's how much internal pressure we can carry and still avoid yielding this tube, okay? While some of you are finishing writing that stuff down, let me make another comment, and that is this. You might notice here that we have essentially treated this thing like it's in uniaxial stress. Some of you may have thought of that. Some of you might not have occurred to you. But I did that on purpose. Why do you think I'm assuming this is like a state of uniaxial stress? There's kind of 2 reasons. The first one is it very well might be in uniaxial stress, okay? The only time that you end up applying a longitudinal stress to these things is if they have the right kind of caps on the end, that those caps are actually having to react against those longitudinal stresses. I didn't tell you what was going on in the longitudinal direction, so it very well might be set up to where it doesn't have to support its own longitudinal stresses due to internal pressure. So that maybe not be the most satisfying answer, but that's one answer that you could give, is that it's very possible that the way this tube is going to be used, it won't need to carry those stresses. Probably a better answer is this one. Given the fact that there's a presence of a crack, right? How do you think this thing is going to ultimately fail? Yeah, you're probably talking about that crack splitting as being a much more likely scenario than there being something else. And when there's a presence of a crack there, it probably does make the stress at the bottom of that little crack, it probably is pretty close to, you really probably don't need to think about the other components of stress as much as that stress that's in the tangential direction. Okay? That still may not be very satisfactory, but we're going to go with it anyway because it's, it probably is going to give us a good enough evaluation of it. And I'll tell you what, it's not necessarily easy for us to figure out what those stress fields are even like at the bottom of a crack like that. So we'll just do it this way with kind of a big view of, how this thing might work. I guess maybe another point I could make on this issue is this. If you were talking about the maximum shear stress failure theory, and you have 2 positive principal stresses, what is it that controls failure in that scenario? Do both of those positive principal stresses, do both of them have a role in when that thing will fail? If both of them are positive and you're using maximum shear stress failure theory. Just the biggest one matters. And which one do you think is going to be the biggest one in this case? probably tangential. It's much more likely to be bigger than your longitudinal. So anyway, those are a few reasons why I'm not spending time thinking about a multi-axial state of stress for this problem, okay? All right, so that's part A, I guess part one of part A. Shall we do part two of part A? Okay, so that part two of part A is basically saying maximum allowable internal pressure at room temperature while maintaining a factor of safety of 3.5 against catastrophic failure due to crack propagation. Let me show you the equations that control that. Okay, so I'll say, we'll say avoiding crack propagation. Okay, it's kind of transitioning into our next problem here. This is the basic equation. Okay, our factor of safety is going to be equal to a factor that is labeled KIC. Okay, and that factor right there has a couple of different names to it. Okay, I'll go ahead and write them down. The most common thing you will call K sub I sub C, you'll see it called fracture toughness. Okay, but another appropriate name for it is a critical stress intensity factor. Okay, and what it basically is, it's kind of a number that behaves as if it's a strength against fracture. Okay. I'm trying to hedge my language on that just a little bit and use that behaves as if, because you can't necessarily think of it as a raw strength. But that's kind of the role that it plays, is this idea of being a strength against fracture. Okay? And then in the denominator, we just have K sub I, which is just, not putting the word critical in front of it. This is just a stress intensity factor. Okay, so what? Well, K sub I sub C has some ways that we can find it, right? We can look up some values for some of our materials and figure out a value for this fracture toughness. K sub I has its own formula that I'm going to put down here. So the stress intensity factor, K sub I, it has its own formula that is beta times the stress, that it's kind of a nominal stress that's being carried, times the square root of pi times A. And let me define all of these little terms right here. So the first one is beta. Beta is called the stress intensity modification factor. So it turns out that for different modes that stress is applied to different kinds of parts, we need to sort of multiply by some sort of a factor. They call it the stress intensity modification factor. You would take the nominal stress and multiply by that, as well as multiplying by this other thing, this pi times A. Pi is just the number pi, so we don't worry about that. But A is a crack length. Okay, and the sigma there is your nominal stress. Okay, so for us to figure out our factor of safety, there's a couple of key things that we have to do. One of them is that we need to find a fracture toughness. One of them is that we need to find this stress intensity modification factor. So what do you think might be involved with both of those tasks? Okay, yeah, so one of them is to find that nominal stress. We've basically made an equation already that found that nominal stress although I guess we didn't make it all by itself. But basically, the denominator of our first equation that we did up here is that nominal stress. So we don't necessarily need to recover that before we're ready to actually use it again. What else do we need to find? Okay, beta is this stress intensity modification factor. There's a chart that's involved with figuring that one out. There's also this fracture toughness, and there's actually a table that we're going to use to figure that one out. All right, so are you ready to do that? All right, I think the first one that I have set up over here is the one for stress, the fracture toughness, okay? Now let me explain this a little bit. Table 5.1 is in your text, and it's basically there to show you that you've got for these, a few of these different kinds of materials, you've got different values that might show up for this stress, this critical stress intensity, or fracture toughness is the other thing that's called. But notice here, this table's a little bit weird because it has two entries here for our material, right? Why would that be? Okay, let me show you why that is. And there's another figure that's not in your book, but I went and found the paper that this data, this stuff came from. And in that paper, there's a chart that shows this fracture toughness for this titanium material. And you'll notice there's a pretty well-behaved linear relationship between the data for, and I know this is hard to read, but down here it says that's yielding strength for the material. And right here, this is fracture toughness. So what do you think this table 5.1, what do you think it's getting at? Yeah, it gives you the tools that you need to be able to interpolate, right? So if you have a different level of yielding strength that you happen to know for how your titanium has been processed, then you can use that amount of yielding strength to interpolate between the two values of fracture toughness that they give right there and figure out what the fracture toughness is for your material. And it's interesting here, the more yielding strength you have, what happens with fracture toughness? Goes down. Why is that conceptually? Okay, cold working does what? Okay, yeah, it lowers the ductility of it, makes it less tough. In other words, you apply a little bit too much more strain to it, it will just start to crack as opposed to yielding some more. Okay, so that's the relationship that we have between those two values. How should we use it? What do we have for our yielding strength? Okay, we have 990 MPa. Okay, and so without belaboring it too much, we can figure this out by basically saying that KIC for us is going to be based on taking, I'll take the one end of the scale for the fracture toughness, 115 MPa square root of meters. I haven't talked about that yet. Are those some strange units? Yeah, those are kind of some interesting units there. But that is due to the fact that this is how cracks behave. You might remember that for our equation that we had over there just a second ago, we have the square root of pi times a. It just so happens that that's how it tends to behave, right? It's the amount of stress intensity more or less tracks with this square root of the length of the crack. So we have parameters then that deal with that as such. Okay? All right, so we have this value, then what? Plus, okay, I'll take the difference between the two values at the ends of that spectrum. Okay, those all have the same units, so I'll take MPa square root of meters just all in one spot, over, and I'll take down here 1035 minus 910. Okay, this is just in MPa. And all this is going to get multiplied by 990, which is our data point that we have, okay, minus 910 MPa. So all I'm doing here is just interpolating. Okay, and once I've interpolated this out, it turns out that this critical stress intensity factor, i.e. fracture toughness, comes out to be 76.6 megapascal square root of meters. Okay. Awesome. So that means that I have now found the numerator of my factor of safety equation that I'm trying to populate. Okay? What do you think I should do next? Okay? And you might be surprised or you might not. There's another chart, figure 530, where we can figure out the stress intensity modification factor, beta. Okay? And this one kind of works and feels a little bit like a stress concentration factor, right? It's not a stress concentration factor, but it kind of feels like one. And so what we need to do is figure out these sort of dimensionless groups that I've got available over here. For instance, each of these curves is defined by an Ri over Ro. Now let me ask you this question. Do you feel like we should use our modified RO that I used before, or should I use my unmodified RO? Okay, I heard some murmuring. I'm going to suggest that we should probably use it unmodified, okay? Because this, this is essentially exactly our scenario that's given on this picture, right? And what we're trying to come up with is more or less something that is a way to account for the geometry of how this thing actually goes together. And I don't see that there'd be any reason for us to decrease the amount of outside radius, given the fact that our situation is exactly what is depicted in this particular picture right here. So I'm going to suggest that what we do is take Ri. For us, Ri was 10 millimeters, right? And what was RO originally before we accounted for the crack? 12 millimeters. Okay, so when I do that, Ri over Ro ends up being 0.833. Okay, so that basically doesn't pick one of these curves. Okay, we'll deal with that in just a second, but right now I'm going to leave that alone. What do you think my next thing I probably need to find is? Okay, A, which is the crack length, over, right, because that's what it's given right up there is the crack length, over RO minus RI. So the crack length, if you remember, was 0.76 millimeters, over RO was 12 millimeters, and RI was 10 millimeters. When I plug these in, I get 0.38. Okay, so now the next step is we need to find where 0.38 is. So this is 0.3 right here. 0.38 looks like it might be somewhere in here. And if I read up from there, it just so happens that where I have this 0.833, look at that. I've got some really nicely behaved numbers, randomly. Just randomly worked out that way. Okay. Notice here, I'm going to live between this point right here and that point right there is going to be somewhere on that line is where my point is that I'm trying to find. Okay, how do I deal with that? Okay, one way of dealing with it is I heard people saying interpolation. I can linearly interpolate between those 2 points. Okay, one of those points is this you know, is this spot right here, and the other point is this spot up here. But we're dealing with a value of our curve of 0.833. So the way that I need to set this up is to say that beta for us is going to be equal to this is 1.6 right here, right? Okay. Beta is going to be equal to 1.6 plus, okay, and then here I'll do 1.8 minus 1.6. Okay, I'll take that and divide by 0.9 minus 0.75. And I'm going to multiply this by the difference between 0.833 and 0.75. To interpolate beta. Okay, and so what comes out of this is 1.71. With me so far? All right, good stuff. So all I have to do now is take my beta factor as well, you know, so that's what I just found right here was beta. Earlier I found KIC. I need to take those over to my calculation and find a factor of safety, or set it equal to a factor of safety so that I can find pressure, really is what I'm going to do. Okay, so we'll go back over here and we'll say 3.5 was my factor of safety I'm trying to hit. This is going to be equal to KIC in the numerator, which was 76.6 megapascal square root of meters. This is going to be divided by a beta factor of 1.71. Okay. All this multiplied by my nominal stress. Okay. My nominal stress, I think if I slide this down, I can see what I had there. 10 millimeters squared times pi over 12 minus 0.76 was just 11.24 millimeters squared minus 10 millimeters squared. Okay. What's the rest of that over there? That's just a factor of 2, right? All of this stuff over here was just a factor of 2. So let me just put a factor of 2 right here. All right. What else do I need in my calculation? Square root of pi times 0.76 millimeters. Okay. Now there's one little tip I need to give you here. Right now in the numerator I've got this factor of square root of meters. In the denominator I have another factor that is going to have square root of millimeters. How do I make those units jive with each other? Okay. Well, keep in mind you can always take powers of the number 1 and it doesn't change what that is. One way of writing the number 1 is with 1,000 millimeters per meter. So I can multiply by that and it doesn't change anything with my calculations, right? Because that's just another way of writing the number 1, right? That means I can also take that to the 1/2 power and it's still the number 1. Right? So if I take a square root of 1,000 millimeters over meters, then that will cause my units of square root of meters to jive with my square root of millimeters that I have in the denominator. Okay? Did you follow that? Okay, so again, I'll spare you all of the calculator typing, but you can put all this in and solve for P sub I. And what comes out of this is that P sub I is going to be equal to 34.49 megapascals. Okay, and you know, here in the United States, we don't know what the heck a megapascal is in terms of like the feel of it, right? So one of the things that you might be curious about, so I'll tell you. The first one that we had up there, turns out that's about 5,402.5 psi. It's a lot of pressure, but it's not unheard of pressure that you could have in a tube like this. And then for my other one that I just calculated here, I'm not sure I actually wrote that one down. But anyway, it's obviously a little bit less than that. So I think I might have it over here. All right, yeah, it turns out to be about right at 5,000 psi. Okay, and the only reason I supply those is so that those of you who have the sort of intuitive feel about PSI, you know, you might feel that a little bit more than what you could sort of mentally think of an MPa. All right, so question for you then, which one happens first? The second one happens first, right? It is more likely that this thing is going to fail due to crack propagation than it is due to the material yielding, right? So here's my question. What could we have done, or what would have been a more beneficial condition of this material given that we know that? I'm talking in big, broad terms, right? Think of this titanium, and it's been cold worked to 990 MPa, right? Don't cold work it as much, right? If you didn't cold work it as much, it would be less likely to crack before it would be likely to yield, all right? So shall we figure out how much could we maybe have cold worked it, or if it had been cold worked to a different level of strength, where would that kind of break-even point have been, right? Where it's just as equally likely to yield as it is to fail due to the crack propagation. How do you think you might go about looking at that? Okay, so what we need to do is, it's also going to happen at a different pressure, right? So like, we're not necessarily going to have the same pressure once we set that strength value to something else. Think of this equation up here, right? And you know, we'll take this equation that we started out with up here. What if we rewrote it? Okay, so I'm going to copy it. But now I'm going to rewrite it. So this is, we're going into part B down here. Maybe. Okay. I now don't know what my yielding strength is going to be, right? So I need to get rid of what I had in the numerator and replace it maybe with S sub y. Do you agree with that? Okay. I can also, you know, kind of move the things around with that factor of 2 right there. And let me show you that we can basically, if we move the right equation, or move the right variables to the right places, I can eventually rewrite this with S sub y times 11.24 millimeters squared minus 10 millimeters squared over 10 millimeters squared minus 3.5 times 2 times P equals 0. All right. So now I have this two-variable equation. If I can find another equation in terms of those two same variables, right, S sub y and P, then I can maybe solve a system of two equations and two unknowns and come up with both P as well as what S sub y is going to be to cause both of these to happen at the same time. Where might I get another equation? Okay. Well, let me actually take this one. Okay. Now, once I take this one of the things will now change for this equation, and that is this fracture toughness. Because keep in mind, the fracture toughness changes when we change the material strength. So I now won't have just a plain value of fracture toughness. I need to express that fracture toughness in terms of my yielding strength. Right? Where do I get that? If I go up here, I actually have an equation that basically does that, already written out right here. So let me copy it, and I'll bring it down here. What would I need to change on that? Which of the numbers in that equation can I no longer sort of count on? 990, right? That's now, I need to write it in here as S sub y. Okay? So, once I do that, I should be able to take all of this stuff and plug it in basically as a factor in the numerator of this equation. So I'll space it out and make it look a little bit more pretty. But move that over. We'll put all of this in here. And I'll put a bracket around all of it, or parentheses. How many variables do I have in that equation now? 2. And they are P and SY. Okay? And it actually is possible for me to rewrite this so that it's in the same form as the equation that I had there a second ago. Okay, actually, I think I had some stuff left over here. That looks like exactly what I have written above. Okay. But, just to sort of save us the heartache, let me do this. It does turn out that S sub y calculates to 979 MPa, and P calculates to 36.84 MPa. Okay? For anyone who's interested, let me actually show you how this thing ends up. So if you write it all out, what do you think my point was in actually showing you how to basically reduce the equation I had here down to there, or at least what the result would be of doing that reduction? Okay, my point with it is you don't need extra special computational tools, because once you have it in this format, this would be the coefficient of one of your variables. So you could put all that into a tool like your calculator, right? Calculate all of that stuff and put it in as one of the as one of the coefficients of one of your variables. This would be a coefficient of your other variable p, right? And what would everything over here be? That would be like your constant term on the other side of the expression. So, you know, that would be for one of your equations, and your other equation would basically have similar parts, right? That would be one coefficient. This would be another coefficient. And then, of course, 0 would be your constant term. So it's just a linear system of equations. Even though it's a little bit messy, all that stuff is doable, and what comes out of it are these results. Your S sub y ends up being 979 MPa. P ends up being 36.84 MPa. And again, you might be interested to know how many PSI that is. That's 5,343 PSI. Okay, so what's our big takeaway then? Okay, by processing this material to a yielding strength of 979 MPa, meaning less cold work, you know, if that had been how that material was processed and it had this crack in it, then we would be able to recommend 343 more PSI than what we could have recommended, or what we could recommend given that it was processed to 990 MPa. Isn't that interesting? So I want us to not miss this big idea here. You can sometimes improve the prospect that a material will withstand the types of load that it needs to withstand. You can sometimes improve that by actually reducing the yielding strength, right? And the reason why is you're making it less susceptible to fracture by doing that, less susceptible to cracks propagating through the material. Isn't that interesting? All right, I need to give sort of one last sort of disclaimer here, and it's this. There is a whole segment of this course that we haven't gotten to yet called fatigue, okay? Fatigue is a different kind of phenomenon. So the big idea of fatigue is that if you have a material that you stress at a stress level that's hypothetically lower than what it would take to break that material, and then you do it over and over again, right? So like my pen here, if I was to not stress it hard enough to break it, right, and then relax it, and then not stress it hard enough to break it, and then relax it, and if I did that 1 million or 2 times, it's possible that my pen would still break even though none of the times that I flexed it did I flex it to a level that would have broken it, right? That's kind of the big idea that we're going to start getting into when we start talking about fatigue. Here's what I want to say about that. When you have cracks in a material and then you subject it to fatigue loading, in other words, repeated loading over and over and over again, what we're doing right here isn't quite valid, right? So this is more for static loading, what we just did up here. If you've got cracks in a material and then you apply this fatigue loading, that is a really bad situation, because what happens in fatigue loading is any place where you have material defects and you load it, you basically can separate those defects by a little tiny bit and then relax it again, and then separate it again, and then relax it again at each of those little tiny defects in your whole material. And what that does, even though we don't see it on a macro scale, what it can do is it can cause a little tiny bit of plastic deformation at the edges of those defects. And over and over and over again, we keep on applying that stress to it. It can make those cracks begin to spread even at much lower stress levels than we would have predicted that they would start spreading. Okay, so we'll get into some of that when we get into fatigue, but I just needed to throw that in as a little bit of a disclaimer on what we just calculated. This is a little bit more for, you know, not cyclic loading. This is for just apply the load and leave the load on it. Okay? Questions before we go? All right. Well, I will see you guys at the next one.